Okay, now we're going to look at the history of life, imagining it as a tree. So some terms to know for this next section are systematics and phylogeny. Systematics is all about classifying species based on common ancestry. So if two organisms had an ancestral species, that is their common ancestor, and they are descendants of that common ancestor. The other term to note is phylogeny, and this is the evolutionary history of organisms. So how are organisms related to one another over evolutionary time? And for phylogeny, we utilize what's called a phylogenetic tree. And these phylogenetic trees show the relatedness of organisms to one another. They are a hypothesis, so they are just an educated guess about how these evolutionary relationships work together. Based on the current morphological information, fossil record, DNA sequencing, it's our best guess about their relatedness. So on the left right here, we have a phylogenetic tree. A couple things to point out. These dots right here represent nodes. So nodes are areas where evolution occurs and there's branches coming off of them. So as we see at this node right here, we have a branch coming off that is our fish group, another branch leading off to another node that then leads on to the birds, to another node that leads on to the humans, to another node that leads on to rat and mouse. So these little vertical stems that go up and down represent the passage of evolutionary time. And when branches come off of a node, that represents the descendants. So the descendants come off of a common node, and those descendants all share that common ancestor. So for example, your rat and your mouse share the common ancestor node right here. And then the rat, mouse, and human share this common node. The bird, human, rat, and mouse share this common node. And the fish, bird, human, rat, and mouse share this common node. So again, all about showing evolutionary relatedness. The important thing to note with these trees is that if they share the node, they have the common ancestor. And it doesn't matter if we draw the tree slightly differently or rotate two of the branches about the node. For example, with our human, rat, and mouse, we have this node right here that connects to the human branch and the branch that leads to the node that connects the rat and the mouse. In this diagram over here, we flip-flop it, so the humans are now on the right, and then the rat and the mouse are now on the left part. However, the rat and the mouse still share that immediate common node, and the rat, mouse, and human still share that second node. So despite rotating the tree and making it look a little different from your perspective, the evolutionary relationship is still maintained. We still convey the same information. Another example with our three domains, which we'll talk about in a little bit, with our bacteria, our archaea, and our eukarya. We have nodes, again, that represent the common ancestor for all those groups. So this node is for all three domains, the bacteria, archaea, and eukarya. This node right here is for our archaea and our eukarya. This node right here represents our protist and then all the groups that descend off of it, leading to our plants with our protist, our fungi with their protist, our fungi by itself, and our protist with our animals. So the one thing to note is that our protist group don't nicely fall into one classification. So we have some protists that are closely related to animals, some that are closely related to plants, and some that are closely related to neither. So it gets a little dicey, and not everything always fits in a nice, convenient tree. Sometimes we have to sort of draw extra branches to represent all the possible organisms. But the tree, again, is the best educated guess we have based on the information we have. And within that tree, we have what are called monophyletic groups. So monophyletic groups are groups where all of the individuals in that group that we're circling are more closely related to each other than individuals outside the group. What that basically means is that from a node, or if we circle a group of organisms, all of those organisms have to share a node, and that node has to contain all the common ancestors. So for example, we have our birds and our crocodiles that I'm circling for this group in question. So the birds and the crocodiles both share a common node, that's A, and that node, A, contains all of the ancestors, or all the descendants, from that node. So birds, crocodiles are both contained by the node, so it's a monophyletic group. If I were to circle birds, crocodiles, lizards, and mammals, so these 4 right here that I'm moving my mouse around, all of those share this common node here. And that node contains all of the descendants. So it contains mammals, lizards, crocodiles, and birds. However, if I were to circle, for example, this box right here around crocodiles and lizards, crocodiles and lizards, yes, they share the common node of B. However, that common node does not include all of the descendants. So it includes crocodiles and lizards, but we left out birds in this case. So that is not a monophyletic group. So with these evolutionary trees, again, we are comparing organisms' ancestry and lineage. One of the ways we can do that is by using comparative anatomy. So comparative anatomy is just looking at structures and similarities and differences, and based on those similarities and differences, grouping those organisms together. So a couple traits we have here with 4 different mammal species. We have possess retractable claws. We have the number of chambers in the ear bone, and we have whether or not they have a penis bone. So on the left side, we have our African lion spotted hyena, and in terms of possessing retractable claws, that's a yes. They have 2 chambers in the ear bone, and then they do not have a penis bone. So they share 3 common characteristics, so we group them together as having a common ancestor. On the other end, with our gray wolf and our black bear, for possessing retractable claws, they do not have that. The number of chambers in the ear bone is 1, and then they do not have, or they do have a penis bone. So they share those 3 characteristics, so we group them together as having a common ancestor. So with comparative anatomy, we can look for similar features of an organism to group them together as having a common ancestor. Another method of doing this is by comparing DNA sequences. So the idea behind DNA sequences is that the base pairs, so our adenine, our thymine, our cytosine, and our guanine, as we learned about when we talked about DNA at the beginning of the semester, we have similarities between organisms. So the more amount of DNA that you share with a fellow species, the more closely related you are to them. So humans and apes and monkeys share a lot of our DNA because they are our ancestors, versus organisms that may have evolved on different parts of the world may have a lot of different DNA sequences. So in this tree right here, species 1 and 2 are closely related because they have only a few differences in DNA pairs. Same with species 3 and 4, but between the grouping of species 1 and 2 and the grouping of species 3 and 4, there's a lot of DNA differences. So they are not as closely related, or species 1 and species 2 group are not as closely related to the species 3, species 4 group as each group is to the members within the group. So for making trees, morphological features is sort of the old-fashioned way of writing trees, and using DNA evidence and sequencing is the more new-fashioned way. And it's largely because similar structures don't always tell if we have a common ancestor. Last week we talked about this a little bit with our bats and our insects. Both of them have wings through convergent evolution because they evolved similar structures due to similar environmental pressures despite not being in the same actual environment. Because of that, we would think, okay, they both have wings, so they must have a common ancestor of some sort. However, when we look at the actual phylogeny, bats are a mammal. They are more closely related to humans than they are to insects, which are way over here on our evolutionary tree. Now, there may be some kind of wingless common ancestor of the bats and the insects, but in terms of immediate lineage, bats and insects don't really closely have a relatedness, which is why it can be not always the best idea to utilize morphological features. You can, but the better way is to utilize DNA sequencing. Another example of that we have, again, with convergent evolution. If we were to look at traits, that would be misleading. So our common true right here that I'm circling and our African golden mole look very similar. They're underground rodents. They have similar body size and structure. However, after we run the actual DNA, the African golden mole is more closely related to the African element than it is to the common shrew, which is crazy to think about because the African golden mole looks nothing like the elephant. They're different in size, in body shapes, and structures, but yet the DNA evidence doesn't lie. It shows us that they are more closely related to each other than two organisms that look the same. So again, hitting home that DNA analysis is a really powerful tool for writing these trees. Okay, so next we're going to talk about this idea of macroevolution and microevolution. So if we take the prefixes, micro just means small and macro means large. So microevolution is on a small scale, macroevolution is on a large scale. Microevolution is all about the change in frequencies over one or a few generations. In the last chapter, when we talked about evolution, I gave you the simple definition that evolution is just the change in allele frequencies from one generation to another. In the grand scheme of things, that's just microevolution. We're just talking about allele changes. So the inheriting of the recessive allele, inheriting the dominant allele, some kind of change from parent to offspring, that's microevolution. Shown here in this diagram, we have moving from one generation to another. That's just a small change. Macroevolution is the accumulated effect of a lot of microevolutions over and over time. So when we talk about macroevolution, we're talking about the large evolutionary scale, which can lead to new species, adaptive radiation, so on and so forth. So macroevolution is lots of microevolutionary changes over time. Additionally, with evolution and microevolution, there is this idea that evolution can be paced either slowly or quickly. So some argue that evolution is what's called, it occurs by creeps, and others say that it occurs by jerks. What that basically means is a creep is slow, gradual change, and a jerk is a quick, rapid change. So we actually have evidence in the fossil record of both occurring. So with gradual change, evolution by creeps, this is when things occur over slow incremental steps. So in terms of our time span, we're slowly changing the allele frequencies from generation to generation, and eventually we will result in new species. For evolution by jerks, we have what's called punctuated equilibrium. And these are long periods where we don't really have a lot of change, followed by a huge burst in rapid change. So we may have similar genetic material passed from generation to generation, and then all of a sudden we have a lot of changes from one gen to another, thus creating new species. So with this process of macroevolution, we have what's referred to as adaptive radiation. So adaptive radiation is when a small number of species or a species ultimately diversifies into a lot more species. And one key example we have of this is the mammalian radiation after the meteor strikes and wipes out most of the dinosaurs. With adaptive radiation, we have an ancestral primitive insectivore. This is basically just an ancient mammal that ate insects. And ultimately, from the catastrophe that wiped out the dinosaurs, we had a radiation into a bunch of different mammals that we know today. So bats, flying squirrels, elephants, cheetahs, moles, seals, you name it. They all came over time from this radiation. So pretty much inhabiting all different types of environments we could think of. So forest, savanna, ocean, throughout history. So another big example of this we have is with our Galapagos finches. With our Galapagos finches off the coast of Ecuador. So the mainland finches ultimately crossed the ocean to those islands and diversified in terms of beak size, in terms of coloring and feathers, and so on and so forth. So one species led rise to a lot of different species. Okay. And there's three phenomena that can trigger adaptive radiation. The first one is the mass extinction event. So some large devastating event that happens over a very quick amount of time and wipes out a lot of species, thus leading to the adaptive radiation of new species. Colonization events, where we can have a species move into or move out of a population, and ultimately lead to a founder effect. So by starting their own new population, eventually evolution will kick in. An example of this is something like birds or small insects flying from the mainland and ending on a distant island group or a new continent. And lastly, we have evolutionary innovations. And these are where there's some kind of key feature that ultimately leads to a lot of diversity. An example of this we have with plants is through flowers. So flowers have a lot of different shapes and colors that allow for plants to effectively pollinate. You can probably think of so many different colors and varieties of flowers that you know. And that's an example of evolutionary innovation creating a lot of species. So going a little more in depth with extinction. Extinction is the complete loss of all individuals in a species population. So we think of we think of extinction as kind of a sad event where a species is dying, but extinction is actually a part of evolutionary history that has occurred many, many times. There's a lot of species that we never had or never even knew during our lifetime that came and went over the hundreds of thousands of millions of years. That's not to say that, however, extinction is always a good thing, particularly when we talk about the rate of extinction. And the rate of extinction is basically the number of species that become extinct over time. So over the gradual course of the evolutionary history of Earth, we have a lot of species that have gone extinct, but that was over a gradual long period. If you have a quick spike and a lot of species are going away in a very quick amount of time, that's not a good thing, such as due to human urbanization and population growth. And we have two categories of extinctions. We have what are called mass extinctions, and we have what are called background extinctions. So mass extinctions are basically when a large number of species become extinct over a very short period of time because of some sudden environmental change. An example of this for mass extinction is when the asteroid hit the Earth and wiped out the majority of the dinosaur species. There can be other examples like huge natural disasters, like floods and earthquakes and so on and so forth. But the idea is there's some overwhelming force that's coming for all the animals, and it doesn't matter about their fitness level. So an organism might be really crafty at running away from predators or camouflaging itself to avoid detection. But if a giant asteroid comes to Earth and wipes everything out, none of that's really going to matter. It's indiscriminate in that fact. The other type of extinction we have are background extinctions. So these occur at much lower rates and they're much more gradual than mass extinctions, but we have them over the course of evolutionary history. So things just like competition between species or human hunting or human overfishing. So gradually over time, that can wipe out a population.